The key to success in solving parts per million and parts per billion problems and those kinds is remembering that these solutions are so very dilute that the density of the solution is approximately the same as the density of the solvent itself. Consider a solution that is 4 parts per million sugar. Now what does this mean? This means that in a million parts by weight, 1,000,000 grams, 1,000,000 pounds, 1,000,000 milligrams, whatever, that 4 parts would be sugar, 4 grams, 4 pounds, 4 milligrams, depending. Aqueous solutions designated in this fashion are generally so dilute that the density is considered to be 1 gram per milliliter. Non-aqueous solutions, such as an alcohol solution, for example, are so dilute that the density is considered to be whatever the density of that solvent is. And if it holds true for parts per million, you may be assured that it is going to hold true for parts per billion too, which is a solution that is even more dilute. Here's a problem. How many grams of lead must be dissolved in acid and diluted to a final volume of 100 milliliters to prepare a 10 parts per million solution? That's 10 parts per million lead. Assume the solvent is water, and therefore assume the density is 1 gram per milliliter. You take 100 milliliters at a gram per milliliter is 100 grams of solution total. Now, I would allow my students to get by without doing this step because I understand the logic that they're using in their assumption that 100 milliliters in this case is 100 grams, and that is a very correct logic to use. I take 10 grams of lead over 1 million parts. That's 1 times 10 to the 6 grams of solution. Where did that come from? That came from that 10 parts per million. Then I multiply that by 100 grams and get 1 times 10 to the negative third grams of lead. Some students get a little confused when it's worked this way and would really rather work it by ratio and proportions. So if you want to work it by ratio and proportions, do it like this. 10 grams of lead is to 1,000,000 parts of solution as X grams of lead is to 100 grams of solution. Do you like that better? Just don't foul up your algebra in solving it. And you will find that X, of course, comes out to be 1 times 10 to the negative third grams of lead. How would you make a 10 parts per million aqueous silver ion solution from silver nitrate? Well, you dissolve enough silver nitrate to provide 10 grams of silver in sufficient water to make 1,000,000 milliliters of solution. But you probably wouldn't get by with just writing that down as an answer, would you? So we need to make a side trip, perhaps, to determine how much silver nitrate that is. Well, we have 107.9 as the atomic weight of silver over 169.9, which is the molecular weight of silver nitrate, is to 10 grams of silver, if you will, over X. In other words, a ratio and proportion. We take the atomic weight of silver to the molecular weight of silver nitrate as 10 grams of silver is to X. And X comes out to be, about a little bit less than 16 grams of silver nitrate. So, to make a silver nitrate solution have sufficient silver to provide 10 grams of silver in 1,000 milliliters of solution, we would need to dissolve 16 grams of silver nitrate. Are there the same number of moles of silver ion and nitrate ion present in 100 milliliters of this solution? Oh yes, in this case there certainly are. There has to be. The silver ion and the nitrate ion are in a 1-to-1 ratio in the compound, and you're getting the silver from the silver nitrate. Let's try this problem. Assume the drinking water standard for nitrate ion is 5 parts per billion. How many milligrams of nitrate is allowed in 1 glass And let's assume the glass is a 90 milliliter glass of tap water. Well, 90 milliliters times 1 gram per mil is 90 grams of solution. Again, whether you have to do it this way or not is up to you and your instructor. 5 grams of nitrate ion over 1 times 10 to the 9th, that's 5 grams of nitrate per billion grams of solution, times 90 grams, that is the mass of the whole solution when you're through, is going to give you 4.5 times 10 to the negative 7th grams. But we didn't want the answer in grams. We wanted to know how many milligrams. So we take the 4.5 times 10 to the negative 7th grams times 10 to the 3rd milligrams per gram and find that what we're dealing with is 4.5 times 10 to the negative 4th milligrams. A tiny amount indeed to make the maximum nitrate allowed in 1 glass of tap water. Parts per million and parts per billion. Brought to you courtesy of Chemistry Professor, offering complete courses in chemistry on DVD. Visit us at our website at www.chemistryprofessor.com.